We have two parts of the algorithm. Okay. The first is the DFS with one parameter, which is the graph. So the input will be the graph, and the output will be labeling of the edges of G as discovery edges and back edges. We have two methods, discovery edges and back edges. If you look at the details, you will see that for every U, which is in the vertices, let's set the label U as unexplored. And then for all E, which is the edges of the graph, let's set the label unexplored. And then for all the vertices, if the label is unexplored, then let's do DFS G, V. So DFS G, V is this algorithm. So this algorithm will be a recursion. So the basic idea is using this recursion on the DFS. So whenever if the node is unexplored, then we will do recursion. So in the recursion, we have the graph G, this one, and then the vertex V of that graph. So the output will be labeling of the edges of G in the connected component of V as discovery edges and back edges. So we will have the D and B. So first, we will set the label V as visited and then check if the E is incident edges of V. Do you still remember what is incident edges? If I have V as a node, so I want to know the incident edges. So if there is any edge, okay, so I will put that one into the loop. So this is for all E, it means for all edges. So if I have like 4 edges, then I will do 1, 2, 3, 4. I will start from the edge number 1, and then I go to edge number 2, and then I go to edge number 3, and then I go to edge number 4. And then I will check if it is unexplored, then let's check the opposite. What is opposite? If I know that this is the V, so I want to know the opposite of V, comma E. Then if I'm now in the edge number 1, I would like to check what is the opposite of this one. If now I'm in the iteration number 2, then I would like to know what is the opposite of this one. Okay. So if the label is unexplored, now let's set it as discovery. And then we call back the algorithm to call again the DFS if it is unexplored. But if it is explored, we set it as packets. Okay. So the discovery edge means I want to set the edges as discovered, or I would like to make it as the new edges, but there will be another edge which is back edge if the node has been visited before, or the edge has been visited. Maybe for the easy understanding, let's see this one. So we have the node or the vertex. Let be the blue vertex is the unexplored vertex, and then let be the yellow is the visited vertex. or I call this is UV, unexplored vertex, and then VV, visited vertex. And then for the edge, there will be two. The black color without the arrow, it is unexplored edge. And then the gray with arrow, it is discovery edge or DE. And then the back edge is the dash with arrow. Now let's see, this is a graph. So every node A, B, C, D, E, every node has been not explored. So it is unexplored. So the state is UV, 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 UV. And then all the state of the edge is unexplored. Okay. Unexplored, 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 unexplored. And now let's start from the first. I want to start from A, and then I want to check the first part. Okay. So in this case, if I want to start from A, if you look at the algorithm, set the label V as visited, and then for all E, which is the incident edges of V. The incident edges of V means if I look into the A, then the incident edges of A is this one, this one, this one, this one. Okay, but I would like to check one by one. First, I would like to check A. A will be visited, and then I would like to check the AB, which is now discovery edges, because it is the first which is not explored, or this is unexplored edge at the first time. But because we visit A, and then this is the incident edge of A, and we want to find the opposite of A. So this is the P, and then this is the incident edge of A, and then this is the opposite of A. So I go to B, then the A will be set as visited. A will be set as visited, B will be set as visited, okay, and AB is discovery edges. Next, I will start from B. When I start from B, again, we will check what is the incident edge of B, and then I would like to check what is the opposite of B. Okay. So if you look at the algorithm, we always have the incident edge, and then if it is unexplored, we check the opposite. And then if it is unexplored, we set discovery. Okay. So first it is checking the incident edge. If it is unexplored, check the opposite. If it is unexplored, we set discovery. Because this one, it is unexplored, so BC now become discovery. So this edge is discovery, this edge is discovery, this one is visited, and this one is visited. Next, I know that this opposite is C, okay, and then from this C, again, I mentioned to you, there are three. First, we need to find the incident edge, and then we need to find the opposite. Okay. So in the C, we need to find what is the incident edges. Okay, we know that this is the incident edges. Okay, let's see what is the opposite. So this is the opposite, A. But there's a question. Is A unvisited vertex? A has been visited. Okay. Because A has been visited, so we call this is the packets. We call this is the packets. Instead of doing this as the discovery ads, this is the packets. So we will not do this as the searching on the DFS. So this is the packets, and then we will go to another incident ads. We will go to another incident ads, and we will check the opposite and make sure that the opposite is unexplored. So D is not visited, or sorry, not unexplored cortex. It's not visited. Oh, this one should be visited. Sorry. So D is not visited. Then we can choose this one as the discovery edge. And then next, from D, we check the incident edge, and then we will check again the opposite. So this incident edge is not explored. Okay, we go this one, but let's check the opposite. The opposite is A. A has been visited. Then, because it is already visited, we make this as the packages. So this is the packages, this is the packages, and then no other incident edges here. We know this is a recursion. In the recursion, if we finish until the leaf, okay, or if we finish until the end, it will return back to the previous. So we return back to the previous node. This is C. So we will check, is there any other incident edge of C? Yes. And then let's check again the opposite, whether the opposite is already visited or not. Because this E has not been visited or it is unexplored, then we set the CE is as a discovery edge, and then we go to this E and put this as the visited cortex. And then after we put this as the visited cortex, again we will check the incident edge. Okay, and then we check the opposite. The incident edge of E is this one, and then the opposite of E is A. Again, A is already visited. Then this incident edge is a package. Do we finish all? After we have in the E, yeah, we finish everything. So in the recursion, we will return back to the previous node. We finish to check all the edges, and then we back to the previous node. So we finish to check all the edges, so we return back to the previous node. And in this node, we also finish to check every of the possible node, then we finish. Okay. So if I return back to the algorithm, so this is the way to check whether the E is unexplored and the V or the opposite of V is unexplored. If it is unexplored for the both, and we will set it as the discovery on the ads. If it is already explored or is already visited, then set the label as the package. If you implement it in the Python, maybe it is easy, like this one. Okay. So for every E, it is the X. If it is incident edges of U, then let V is the opposite of U. So if V is not in the discover, so if it is not visited, then discover V equal to E. And then, yeah, we will do the loop again. So the Python implementation will be like this one. Now, what we want to know next is how we can apply this to application. Yeah. So when you want to make a kind of game like maze, we can apply the DFS. So this DFS is similar to a classic strategy for exploring a maze. So we can mark its intersection, corner, and dead end as a vertex. So this is intersection, this is a vertex. Dead end, like this one, it is a vertex. Corner, this is also a vertex. This is a vertex. So if you have all the vertex, we can define what is the x. So let's say this is another vertex. Then we can have this as an x. This is another vertex. 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 So you can define many vertex, and then you can define many edges. And then you can check whether these edges already discovered or not. Okay. And then you want to check for all possible discover edges until the exit. So we keep track of the path back to the entrance, which is the start vertex, by means of a row, or we call this is the recursion with stack. So in the DFS, we visit all the vertices and the edges. So as you know from the example, we visited all the edges and we visited all the vertex. In the property 2, the discovery edges labeled by DFS G, B form a spanning tree. So it is the spanning tree of the connected components of B. So if you make all this one, after the DFS, you can see this is a spanning tree. So the A, it goes to B, it goes to C, it goes to D, and it goes to E. So it is a spanning tree. Okay. Let's forget about the back edge and let's see from the discovery edge. So from this discovery edge, this is a spanning tree, and we can use to determine this is the path, the possible path. When we do the analysis of the BFS, when we set or get the vertex or the edge label, it takes O1. And each vertex is labeled twice, whether it is unexplored or it is visited. And each edge also labeled twice, whether it is unexplored or it is discovery or it is backend. And the method incident edges is called 1 for each vertex. So that means at least there will be one time for incident edges. Then because we will run for every node and for every vertex, and yeah, this exploration we just have, if I mentioned before, we just call the incident edges, and then we call the opposite. Okay. So it means the loop will be n times it is the number of vertex, and m times it is the number of edges. That's why we can have n plus m time, provided the graph is represented by adjacency list. Do you know what is adjacency list? Okay, you can look at the previous materials. We have three kind of structure. Adds this, and then we have adjacency list, and we have adjacency matrix. Okay, so these three structures in the graph you need to remember. Okay, so this four moments O n plus m, it is for the adjacency list. Okay, and you already know from the properties of the graph, we can have like the summation of the degree of V will be 2 multiplied by m. This is the property in the adjacency. We can use this BFS as path finding. You know path? Okay, we want to find a path or a traverse from V to Z. Okay, and we can specialize the DFS algorithm to find a path between two given vertices U and Z using the template method pattern. So in this case, we can start U as the starting vertex, and then we can use stack. You already learned stack in the first chapter, maybe before the mid-exam we learned about the stack, and the stack is used to keep the track of the path between the start vertex and the current vertex. As soon as the destination vertex set is encountered, then we return the path as the content of the stack. So yeah, if you use the stack, you push, you set the label visited, and then you push the V. So if V equals to Z, it means if the starting vertex equals to the ending vertex, then finish. If not, we will do this one. So we will check what is the incident element, the incident edges of V. So every of this BFS will have the incident edges. Okay, we will check for every incident edges, and then we will check the opposite. We will check the incident edges, and then we will check the opposite. If it is unexplored, then set the label as discovery, and then push into the stack. After we push, we will do the recursion. So we will check the next possible vertex. And so on. After we finish this one, if we will pop the E, so we will put all the things. If we already visited, then yeah, we don't need to visit it again. And if we have the opposite as explored, then we will make the label as backends. So at the end, yeah, we will pop the V in order to know what is the remaining element in this one. So the remaining element will be all the element that you can use for the path finding. You can also find the cycle. The cycle means we want to know the V and Z. When we have the V, it will return back to the V. So we can specialize the DFS algorithm to find a simple cycle using the template method pattern. So we use the stack again to keep the track of the path between the start vertex and the current vertex. As soon as we have the back edge, okay, the V and W, if we have the back edge, we return the cycle as the portion of the stack from the top of vertex W. As if you remember from the example, if you remember from the example that I have before, let's say from A to B, B to C, and then we can have this is the cycle. Okay. But actually in the DFS, we want to explore all nodes. We want to explore all vertices before determining this is a cycle. Then when you have the label with this unexplored, we will set it as discovery, and then we will do the next. We will do the next cycle. Yeah, this is connection with the path. Yeah. If it is already explored, then we will make a new empty stack. So this new empty stack, yeah, we will check this one until the element O equals to W. Then it means after we found that the vertex already visited and then all the edges already explored, then yeah, we will return this element. So the cycle BFS will utilize the path. So it is the combination between the cycle and the path. Okay, that's about the DFS, and let's move to the next section, which is about BFS, breadth first search. So the idea of the BFS or breadth first search, okay, it has similar to DFS, which is depth first search, but it has some different properties. So in the breadth first search, we need to understand about other kind of graph. In this first concept definition, I want to explain about the path graph. We call it, this is path graph or the linear graph. It is a path with at least two vertices is connected. So I have two vertices. If these two vertices is connected, okay, this is a path graph. At least two vertices is connected. And at least has two terminal vertices. What is terminal vertices? This is the vertices that have degree 1. So let's say this one is a vertex with degree 1. This is a vertex with degree 1. So we call this is the terminal. So we call this is the terminal. So it is the same concept like the bus. If you use bus as the public transportation, we have the bus terminal. Okay, so the bus terminal will be the pool of all buses. In our school, we have the bus terminal because our school is the end and the starting point for some buses. Okay, so yeah, we can think like that. So while all others, if any, have 2 degrees. So this node, this node, this node, and this node have degree 2. So we call this is the path graph. Paths are often important in their role as subgraph of other graph, in which case they are called paths in that graph. So we can see this one, this is a path in the graph. Or yeah, we can have also another kind of graph. For example, this is a path in the graph, okay, and so on. We have another kind of graph, we call it bipartite graph. The bipartite graph or bigraph is a graph whose vertices can be divided into 2 disjoint and independent sets. So here is U and then it is V. So the vertex in U is different with the vertex in V. And such that every X connects a vertex in U to one in V. So this one should have one connection to this V. This U should have connection at least to one of this V. So this bipartite graph are used extensively in online space. So you have the Instagram, you have Facebook, you have other kind of social media. Yeah, we call this is the bipartite graph. We can have the connection of like one community to another community, or one node to another node. It is for the, for example, advertising. It is for the e-commerce, for the similarity ranking. So in the bipartite graph, usually it is denoted as U and V and E. So U and V are the set of nodes. Okay, so this is a set of nodes. This is a set of nodes, and then E is the set of edges on that graph. So I want to know what is the connection between this and this one. In the e-commerce, we can also see like this kind of graph. It means I want to know the users. Let's say you always do the online shopping. Okay. The users bought items. So user 1 bought 5 of item 1. Let's say this is the item, maybe bag. So the user 1 buy bag for 5 items. Maybe this one is ramyeon. The user 1 buy ramyeon for 1 item. Okay. And we can put this one as a graph or the bipartite graph. So user 1 has 5 on the item 1. User 1 has 1 of the item 2, and so on. We can make the graph structure stack. So the graph can be in the stack. We call a graph structure stack, or GSS, is a directed acyclic graph. Directed acyclic graph. What is it? We know the graph is directed graph and then undirected graph. If it is directed graph, we have the arrow. Okay, we have the arrow. If it is directed acyclic. You know what is acyclic? It is no cycle. Okay. So if the graph is directed and there is no cycle, then we can use it as the graph structure stack. So it is its directed path represent a stack. Okay. So in this case, I will go from 7, 3, 1, and 0. So I can represent this one as a kind of tree. So 7, 3, 1, 0. This is a path. Or 7, 4, 1, 0. It is a path. 7, 5, 2, 0. It is a path. And then 8, 6, 2, 0. It is a path. What is the application? So one of the application is the context-free grammar. In the text mining, or now I think you know about the ChatGPT and etc. So they also apply this kind of graph. For every word, they can distinguish this word as whether it is adjective or singular noun, or it is singular verb, or it is adverb, and then you will check what is the best path to make a sentence. So we call this is the graph structure. So you can use the graph traversing with stack. So this is one of the application. If you why the ChatGPT, they can do very well on the finding the correct words to make a sentence. So they also apply some kind of stacking. Even though in the details, there are also some deep learning method inside, but they also apply how to select the proper words for the answer by using stack. So the DFS, we can use the stack. Okay. So the stack, I think, is similar to the stack that you already learned before. If we have the S as the starting, okay, and then we want to know what is the first neighbor of S. The first neighbor of S is T. Then I will put T inside. And then visit the neighbors of the neighbor. So I know that the neighbors of T is, for example, V. Okay, I put again into the stack P. So every time consider the neighbors of the last vertex visited. So T, and then I know V, and then V, I know W. Okay, I know W. I can check the U. So it depends how you can determine the incident X. So after you put everything in this stack, then okay, if there is no other possible node, then it means this is the ending. We can also do with the queue. If we do with the queue, then it means after we put into a list, then it will go out first. If it is stack, first in, last out. If it is the queue, then first in, first out. Okay, I guess due to the time, I will stop here, and please check the class for the learning check.